Hello, and welcome to our third video on the extent and rate of dissolving for our self-guided solutions unit. I would recommend that you visit pages 407 to 415 in your textbook to get some more background on the things that are going to be discussed in this video. This video is going to help you fill in pages 5 through 8 of your self-guided packet, including a practice worksheet for that last page for you to really see if you are getting all the information that you need. All right, so let's just start real quickly here about our solution phases. Just want to mention here that solutions are not just dissolving solids into liquids. We have all different phases possible. And so one of the things we want to remember is that a solution really is just an evenly distributed collection of two or more different phases that mix together equally. Not equally necessarily, you're not going to have the same amount all the time, but evenly distributed. So remember our two terms that we've learned, that the big part of our solutions are going to be called solvents, right? And the little parts are called solutes. So let's just look at some examples here. So the first example we have here is air. And air, of course, is not just one gas, it's a mixture of many gases. The gas that's present in the biggest quantity is nitrogen. So we would say our solvent is nitrogen gas. And then we have other gases there too as our solutes, oxygen being second in line, but then a lot of other gases too in our air samples. So this is a gas-gas solution. So if you hear some chirping here and there, you will notice that Jace likes to be a part of our videos. He always comes in and joins me when he hears my voice. So just a little entertainment there for you. All right, so for our next example, we have fog. So fog, the most common, biggest part of that solution, again, is going to be a gas. That's our air. And when we have fog, we have water droplets in the air. And so we have liquid here. And I just put up our next one here. You can see an example of a solvent of gas with solid particles in it would be something like smoke. So smoke is going to have little particulate parts from incomplete combustion, and that's going to give us our gas solid solution. Sometimes we have liquids with gases in them. We all enjoy this. This example is our soda. So we have carbon dioxide mixed in with water and some other things. And then the next example here, alcoholic beverages. Those are not just pure ethanol. They actually are some kind of a mixture of a solvent that's probably going to be closer to the solvent being water, unless it's a really strong alcoholic beverage. And then ethanol and some other things, of course, are going to be dissolved in those. So this is a liquid-liquid solution. So probably the most common one that we'll encounter is the liquid-solid scenario. So when we have a solid like salt or sugar and we dissolve that in a liquid like water, that's going to be a very common example for us. Okay, so salt water is a good example of that. And you're going to encounter those an awful lot in this chapter. Some less common ones would be things like marshmallows, which actually are solid crystalline sugar, maybe not crystalline, but sugar molecules with gas in them, right? So we've got our marshmallows. And then another unusual one would be an example of a dental amalgam. This is what they used to fill cavities with, a dental amalgam of silver and mercury. And if you recall, silver is actually a solid at room temperature, and mercury is a liquid at room temperature. So this is the rare example of a solid liquid solution. And we can also have solutions where both quantities are solids. And so in that case, we're looking at things like, for instance, brass, bronze, steel, different combinations of typically metals that are evenly distributed, again, to make a solution. Okay. So the next few slides, I'm actually going to take my picture out of the screen so that you can just listen to my voice of a recording that I did before that adjoins these notes. So make sure that you're listening and taking careful note of what is being said here. And so I'm going to pause briefly, if I can do that, and get us set up for this part.
So this lesson in particular is really going to focus in on how much of a substance we can have dissolved in a solution. So probably the best picture in your mind to have is that salt in water, or maybe sugar in water, maybe even sugar in coffee. That's why I have a coffee cup drawn here, to help you picture kind of what we're talking about. When we are looking at how much is dissolved, there are different ways to describe certain scenarios. If we say that our solution is unsaturated, we have to understand that what that means is that we have less than the maximum amount of solute dissolved. In other words, there's room for more. You could picture maybe just putting in a half a teaspoon of sugar into a cup of coffee. Could we put more sugar into that coffee and have it dissolve? Probably. So that is a way that we can test to see what we have in terms of saturation. If we insert an extra crystal into a solution and it dissolves, must be there was room for it to dissolve in there, and we would call that solution unsaturated. So if we have a solution that has the maximum amount of solute dissolved, we're going to call that type of solution saturated. It's really hard to hit this perfectly, but if we had just the right amount dissolved, what would happen if we inserted an extra crystal? It would just go right down to the bottom and sit there. It would not dissolve because there's no more room for extra solute to dissolve in that particular solution. What's probably going to be most common, however, is that we'll come upon a solution that already has some solids sitting at the bottom. If you have solids sitting at the bottom, you would have to assume then that we have met that maximum amount and then some. We have some excess. So if we have a the important thing to remember with that situation is that things don't stop happening ever, really, in our world. And so we want to remember that we have a system that actually becomes at a dynamic equilibrium. We're going to be studying equilibrium in our next topic, but it's good to kind of get a feel for this now. What that means is even though we have some stuff sitting at the bottom and we can't really see anything happening with it, what actually is happening is that we have things coming up off of the bottom and dissolving into solution. But because this is a saturated solution, when that happens, we're going to also have things joined together and end up sitting on the bottom, resolidifying essentially. The rate of these two changes happening at equilibrium will be equal. We'll have as many things dissolving as are resolidifying. So there's no net change visible, but we have to realize that there's constant dissolving and resolidifying occurring. Again, saturated, maximum amount of solute. The way to tell is to add an extra crystal. If it just falls to the bottom, then your solution is saturated. Sometimes I hate to even mention this third vocabulary term because students think that anything that's saturated, as soon as you get more stuff in it, becomes supersaturated. This really isn't the case. What you have to realize here is that for a solution to be supersaturated, it's kind of a complex process. It's uncommon, in other words. What we have to do is heat a substance up, get a whole lot of solute to dissolve in it, and then cool it carefully without any disturbances. When that happens, if the solute stays in solution, we'll have a very unstable situation where we have more than the maximum of solute dissolved than normally would be at that particular temperature. So the system is unstable, and what will happen is if we disturb that system at all, it will automatically bring all those excess dissolved solute particles out of solution, and they will recrystallize.
So we will be seeing an example of this in class, but the important thing to remember is that it is uncommon and it does have to have these certain processes done in order to accomplish it. So most of the time, if you have a lot of solute in a solution, that is going to be a saturated solution, not necessarily a supersaturated solution. Again, we'll see this in class. If you really can't wait and you want to see a video of it happening, you can go ahead and check out that link that you see there at the bottom.
Okay, what we want to look at here is what kind of factors are going to determine how much of a solute will actually dissolve in a solvent. So there are a few things that we need to keep in mind. First, some things just happen to be more soluble than others due to their structure, how they bond together. And so the nature of the solute is really talking about the solute itself. And you wouldn't necessarily be able to predict this without more information, but what you do have available, remember, is Table F. And Table F is going to be able to tell you whether things will dissolve or not in terms of ionic compounds. So you can always check that out, and you can see which ones are going to be more soluble than others. You could also change the temperature of your solution. And here it gets a little tricky because it depends on what kind of solution you're talking about. If you're dealing with solid substances that you're dissolving in a solution, again, here picture like sugar, putting sugar into your coffee, you can actually get more sugar to dissolve in hot coffee than you can in cold. And that's probably just intuitive to you. When you think about having like iced tea, oftentimes it's hard to get that sugar that you put in to dissolve. That's simply because of the temperature. So the warmer we are for our solutions, the more solute that are solids will dissolve in those solutions. The opposite, however, is true if we have gases dissolved in liquids. So think about your sodas. What would be the fizziest soda? What would have most carbon dioxide dissolved in it? That's going to be our cold sodas, and that's how we typically like to drink them. As soon as you warm them up, you're going to see more and more bubbles of gas leaving that solution. And so there's an opposite situation here with temperature. To get more solute to dissolve in a solution with a solid solute, you want to increase your temperature. But to get more gas to dissolve, you want to decrease the temperature. And then finally, pressure. Now, pressure is only going to affect those solutions that contain gases. So again, maybe you're thinking of your soda in this case. Think about what happens as soon as you remove the cap of a 2 liter of soda. You're going to see a bunch of bubbles form as that carbon dioxide begins to leave the solution. And that's because originally your solution was under high pressure, and when you remove the cap, you change your pressure back down to atmospheric pressure. So what do we say for getting more gas to dissolve? Think about it. You need to push that gas into the solvent. And so the way we can do that is have higher pressure. And that is exactly what they do in the soda companies to get more carbon dioxide to dissolve. They prepare that soda under high pressure, seal it off, and then sell it to the consumer.
Okay, coming back at you here with how much versus how fast. So far we've been talking about how much solute we can get to dissolve in solution, but sometimes we also want to talk about the rate of dissolving. How can we speed up the dissolving of a solute into a solvent? So you have to remember that there's a difference between those two concepts, right? Solubility, when we talk about that, we're talking about how much of a substance will dissolve, versus how fast something dissolves. Now that's a different matter, and we have to look at some things that we can do to make things dissolve more quickly. So there are three factors that we can employ to increase the rate of dissolving. Again, this has nothing to do with how much we can get to dissolve, but instead, how can we get things to dissolve more quickly? First thing, might not be a surprise, we could stir it, right? So if you put in sugar into your coffee, you probably are going to stir it just out of just pure common sense, right? To get that to dissolve quicker, you actually want to stir it so that you are creating more exposure of the solute to that solvent. Sometimes we call this agitation, right? So we're agitating our solutions to get them to dissolve faster. We can also increase the temperature. Not only will that fit more solute in it, but it also will allow our substances to dissolve more quickly. So this is kind of like a double whammy with temperature. When you think about it, as we increase the temperature, we're increasing the movement of our particles. So again, we are able to increase the exposure of those solution components to each other. And then finally, we could decrease the particle size to increase the surface area exposed to our solvent. In other words, powders are going to dissolve faster than large chunks. So think about this a little bit. If we put in a large chunk of solute, we can only access that solute. The solvent particles can interact on the outsides here of that solute. But if we break this big chunk up into lots of little chunks, now we can get inside here of this sample and actually have a lot more exposure to that solute by the solvent. So if you want a good picture in your mind, this would be an example of dissolving a sugar cube versus dissolving some granular sugar. That granular sugar is going to dissolve more quickly. Okay, now for this part, we are actually going to have to learn how to read yet another table. And this one is called the solubility curves at standard pressure. You will have available to you this curve on the test. And it actually is in the Regents reference sheet. So you'll have this for your Regents exam as well. And we have to be able to read it. So let's just kind of orient ourselves a little bit here to the axes first. If you look at these axes, you're going to see right here that the y-axis is solubility. How much of a solute will dissolve? Now, in particular, what this is graphing is the grams of solute that are able to dissolve in 100 grams of water. And so if you're asked about 100 grams of water, you can use this table just as it is. And if you're asked about different grams of water, then you may have to make some adjustments, and we'll do a practice with that. Of course, this depends on temperature because, as we said before, as temperatures change, we can get how much of our particles will dissolve to change as well. So for this one, I'm going to focus in on just one of the samples. As you can see, this is a very busy graph. The easiest mistake to make on this graph is figuring out which lines are standing for which substances. So always really take your time and look at where these arrows are pointing. So notice this arrow right here is pointing to the line, which is right here. And this line is for sodium nitrate. I could draw this. It's a little hard working on my graphics tablet again. So when you decide what substance you're working with, you can kind of ignore all the other lines because it gets very busy very quickly. But if we focus in on the substance that we're being asked about, and notice here in number 1, we are looking at sodium nitrate. We want to realize that anything that falls on this line on the graph is going to stand for the saturated amounts of a solution. So in other words, the line is showing us exactly how much solute can fit into 100 grams of water at a particular temperature. If when we look at our graph and we plot a point that is above that line for sodium nitrate, what that would mean is that we are saturated with some excess solute that isn't dissolved. Okay. Now, this is where students sometimes want to say, well, if we're above that line, we're supersaturated. Only if you are told that very particular things have been done. So if you heat up that solution and you get all this excess to remain in solution when you drop it back down in temperature, only then would you be supersaturated. So 9 times out of 10, you're simply saturated with excess undissolved solute particles up in this area of the graph for sodium nitrate. If you are beneath the line for sodium nitrate on this graph, you are going to be in a situation where you are unsaturated and you could fit more solute into solution and get that to dissolve. And how do you know what you would have to add in? You would look and see how close you are to this line at that particular temperature and figure out how much would need to be added in to get it to be saturated. So keep all of these things in mind when you're answering questions. And just to remove some of the busyness, I'm going to kind of erase things here for a moment so that we can focus in on answering these questions. Okay. So number 1 says, how many grams of sodium nitrate are required to saturate 100 grams of water? That makes me happy because now I can just read the graph as it is at 40 degrees Celsius. So first thing I do is I come down to 40 degrees Celsius and I start traveling up the graph until I hit the line for sodium nitrate. And again, focus in, make sure you're on the correct line. So if we're asked for how many grams are required to saturate, then we want to actually read where this line is on the graph at 40 degrees. And so I'm going to pull it over here. And to me, it looks like it's maybe just a little bit above halfway. So I'm going to say about 106 grams of that sodium nitrate would be in the solution. And notice it is kind of weird. We actually have more sodium nitrate than we do water. But again, typically water is going to still be considered that solvent because it is the thing that's doing the dissolving. So just like with everything else in chemistry, we can have some kind of odd results here. But notice for number 2, it's asking about sodium nitrate again, but this time it is saying we've got 200 grams of water. So if we have twice the amount of water, it shouldn't surprise you that we're going to be able to fit twice the amount of solute into solution at the same temperature that we were looking at for number 1. And so simply what would I do here? I would take 106 grams and multiply it by 2. And that is going to give me around 212 grams. And we're graph reading, so you're going to try and be close with your readings, and we may have a little bit of wiggle room there for what would be a correct answer. Okay. All right, so not too bad. And oftentimes you'll be asked about logical different amounts of water, but if for some reason they gave you something strange, like, I don't know, 137 grams of water, notice that up here, you actually have a conversion factor that you could use to make that adjustment, right? So if we know 106 grams will fit into 100 grams of water, we could figure out using dimensional analysis how many grams of sodium nitrate we could fit into any amount of water, okay? All right, so let's have a look at number 3 and see what other kinds of questions we might be asked. How many grams of sulfur dioxide? Now we're going to be working with a different substance, and notice I'm given the name, so I have to recognize what the formula is. Notice that sulfur dioxide is this line way down here. Are required to saturate 100 grams of water. Oh, that makes me happy because I can just read the graph at 10 degrees Celsius this time. Okay, so I come down here to my 10 and I come on up to my graph and I'm asking for the saturated amount. So I'm simply going to read that graph. And here's where, again, a little wiggle room. Looks like it's a little bit more above half. I might say something around 7 grams of sulfur dioxide is going to be in a saturated solution at that temperature in 100 grams of water. All right, so let's have a look at number 4. Number 4 says if 30 grams of potassium chloride, let me come over here and find potassium chloride. That's KCl. Remember, we have to be able to recognize formulas. Looks like this one right here. All right, there's a lot of lines in here, so you're going to really have to orient yourself and make sure that you're reading the correct one. Is dissolved in 100 grams of water. Oh, that makes me happy. I can just read the graph. How many additional grams of potassium chloride would be needed to make the solution saturated at 80 degrees Celsius? So I'm hoping the first question you might be asking yourself is, well, gee, how much does fit into a saturated solution at that temperature for that substance? So now I'm going to come over here to my 80 degrees. I'm going to kick it up to my KCl, lots of lines. Make sure you're reading the right one. It looks like right there. Oops. Sometimes I push a button and I don't mean to. There we go. Get out of there. Oi, there we go. Okay, so now I am going to read this at 80 degrees again, right here. And it looks to me like we're a little bit above the 50. So I'm going to say I could fit about 51 grams of that KCl in 100 grams of water at 80 degrees Celsius. But remember, up here it says we already have 30 grams dissolved in there. So we can subtract the 30 grams that they already have dissolved in there to figure out how many more grams I would have to add. All right, so to me, it looks like here we've got 21 grams of additional KCl that would be needed to saturate that solution. So those are just some examples of the types of questions you might be asked about this graph, and you just have to practice and be able to use it. One other thing to notice here is that most of the substances on this graph start low and end high. As temperature is increasing, notice the solubility for most of these substances is increasing. But do you see 3 lines here that go down instead of going up? So check those out. I think maybe you will notice that HCl goes down and NH3 goes down and SO2 goes down and then kind of levels off a little bit. So what would I say here? I would say HCl, NH3, and SO2 are the 3 substances whose solubility decreases as the temperature increases. Why do you think this happens? Well, if you're paying attention in the prior slides, remember what types of substances actually become less soluble when we increase the temperature. These must be gases. And they are. These must be gases that will dissolve in water and show us this trend. Okay. So what you have to do now is have a quick review and then some practice. So let's just review really quickly. What can we do qualitatively to increase the solubility of our solids? Well, again, looking at that graph, most of the lines went up with temperature. So if we increase our temperature here, we would be able to get more to dissolve. Remember, solubility is talking about how much will dissolve, not how fast things will dissolve. If we were asked that question, we could talk about increasing the temperature, increasing the surface area by decreasing the particle size, and also stirring. Okay. Now, this next question, what can we do to increase the solubility of a gas in a solvent? Remember, gases are different. These ones, we're going to want to decrease the temperature. And we can also bring in that pressure factor since gases are more affected by pressure. And for that, to get more gas to dissolve, we want to increase the pressure on our system there. So now it's up to you. You need to do practice with solubility curves on page 8 in your self-guided packet. And be sure to check your answers, which are located at the bottom of that page. Get some good practice, and if you have questions, certainly ask me in class.